Okay, we're going to be talking about chapters 4 and 5, or basically what I would like to think as let's justify the existence of atoms, what's inside of them and how do they work, and then the hydrogen atom in particular. I'm going to be focusing primarily on some of the formulas because I would like you to understand what is it that you really need to fully be prepared for the exam, okay? So for example, we have here formulas for converting wavelength to frequency and why the formula, so here speed equals lambda times nu, it will be the formula that we will later use, like c equals nu over lambda, okay? So lambda is the wavelength, nu is the frequency, and that gives you an idea of how things are going to be working. We're talking about different types of waves, water, sound, light, and chemical. And that's because when what's going to happen soon, and you know because you have been to the class, we have been discussing this, we're not going to be able to talk about electrons and protons as discrete particles. We're going to have to be considering them as waves. And so the question of where is the electron no longer will make sense. Okay, the electron will become a wave function, and that wave function is distributed about the atom in very specific ways that we call orbitals. But more about that later. At the beginning of chapter 4.1, we're talking about waves, properties of waves, how waves move in space. We're going to talk about light and electromagnetic radiation. And electromagnetic radiation has an electric field and a perpendicular magnetic field. Then in this figure, we see that the wavelengths, come in various different sizes. So visible light is about somewhere between 0.3 and 0.8 microns. Here, of course, this is plotted in terms of wavelength, and as I indicated in the class, wavelength representation is pretty much does not make any sense. We should be representing this in terms of an energy scale. When you represent this in terms of an energy scale, you see that the visible spectrum is not so narrow. I don't know why people keep insisting in plotting in terms of wavelength, but it pervades most books. Okay, so we get here to an expression. Before 4.1, we see an expression that has an electric field equal to an amplitude of the field, Emax, and then we have a cosine function, and cosine functions is something that we associate with waves. And then it has 2 pi x over lambda, where x over lambda is going to be similar to the wavelength, except that you need to multiply times 2 pi. And then we have minus the nu, which is the frequency, times t. Again, if you multiply 2 pi times nu, then you get omega, and that'll be the oscillation frequency. So there's two terms, angular frequency and just frequency. Frequency nu is what the book is using, and I'm fine with that. And here we get to the formula, c equals nu times lambda, and we have the speed of light. It's okay that you use all these numbers for the constant. This is turns out that the speed of light is something that we know very accurately. However, for most of the problems that we're going to be dealing with, 3 times 10 to the 8 meters per second is pretty good. Okay, I'm not going to be going for the ultimate precision, unless I specify in the problem that that's the case. Okay, so we see in figure 4.5 that white light is composed of many different colors. And we have here an example of how you convert wavelength into frequency into wavelength. And then in figure 4.6, we see an explanation of a very important property of waves. When waves are in phase, they add up constructively, so you end up with a much taller, let's say higher amplitude. But when they are out of phase, they cancel each other, and you end up with no wave at all. This is a property exclusively of waves. So we know if we have two particles, then 2 particles is twice as much as 1 particle. So in a sense, the increased intensity, is similar to particles. However, there's no such thing as phase. So, there's no way that one particle is going to subtract another particle. However, with waves, it does happen. So you can have one red light being canceled by another red light. And you can think about this as noise canceling earphones, right? So the earphones are going to be detecting the outside light, sound, and then they're going to create a sound wave that is opposite to the sound that is the noise. And when you add both of them, they cancel, and so your ears can no longer hear the outside noise. Okay, so that's noise canceling, and this is a property of waves, and of course sound is a wave. Okay, the top experiment is known as Young double slit experiment, and it's a perfect explanation for this interference or cancellation of a wave amplitude, right? And this experiment was famous because it demonstrated that light is a wave. And remember that Newton had indicated that light was a particle, and so this experiment really proved that light is a wave. Okay, so then we now switch to quantization in atoms. And the first experiment here is the black body radiation. By the way, in terms of the preliminaries to quantum mechanics, I recommend that you see the other video that I recorded. But here we see the black body radiation. Once again, it is plotted in terms of wavelength, which in my mind makes no sense. And well, I mean, it's accurately depicted in terms of wavelength, but one cannot try to understand what's happening because it's not plotted in terms of energy. Frequency, which is in the top, is just added there as a reference, but it's not linear in frequency. So here we cannot see that as the energy gets larger, we expect to see more and more and more light. So in principle, we should see an infinite amount of light with infinite amount of energy, and that doesn't make sense. However, there is an important point. This black body radiation was being discussed before 1900, and before 1900, we didn't have a connection between the wavelength of the light and the energy of the light, right? And that if you don't have that connection of energy to the color of light, then you could not have seen this why plotting in terms of energy was going to make so much sense. And one of the people that started doing this was Rydberg when he was trying to explain the emission from atoms, which we're about to see. He's the one that realized, wait, if I plot in terms of wave numbers, meaning how many waves, how many wavelengths per centimeter, then things make sense. And turns out that wave numbers is a measure proportional to energy, just like frequency is proportional to energy. Okay, so it turns out that Max Planck was the person to look at this. And I was reading a little bit about Max Planck, and as I indicated earlier, Max Planck derived his formula using Boltzmann statistical mechanics. So in Boltzmann, you have this e to the minus energy of a discrete element divided by k Boltzmann t, and that's exactly what was used by Planck. So let me see if we see this here. Yep, here it is. And so I'm going to use my pen. Oops. Right. So if you see here, so from Boltzmann, we know that e to the minus the energy of a discrete element, so we're going to call it e here, some kind of e, divided by k Boltzmann t, exactly what you see here. And so in a sense, what Planck imagined was discrete emitters. He did not exactly imagine what is written here in the book. I think people give him way too much credit. Even Planck did not give himself that much credit. Okay? So when we go back to here, the description, they're describing oscillators, and that's because they consider that that Planck was imagining discrete oscillators. I have a little bit of a question about that. But basically, it turns out that these oscillators have a natural frequency, and the natural frequency being nu. And so they have discrete levels, and the energy of the level is described by equation 4.3. So n times h, which would be Planck's constants times nu. Okay, and so we end up with Planck's formula. By the way, you know that the exam is going to be you are allowed to bring a formula sheet, and so you can add this formula. That'll make you feel more comfortable. You can write down the number for Planck's constant, 6.6 times 10 to the minus 34 joule times second, because they may become useful in the exam. So here, the book makes an assertion that classical energy is continuous, but quantum energy is quantized. And that to me, again, doesn't make a lot of sense. I can take a white light bulb and I can find photons of energy, any energy I want. So basically energy is not quantized. And so, we can argue about this point in particular. What is quantized is the energy of many quantum mechanical models. Okay, and that's a different story. As we will see in this class at least two different models. We will see the particle in the box and the hydrogen atom. And the particle in the box, we get as a solution discrete energy levels, and definitely that's a quantized solution. So emission or absorption of light from a particle in the box type system would be quantized. Similarly, in the hydrogen atom, we will see that all of the bound levels, as long as the energy is below zero and you are in a bound state, the energy is quantized. However, once you eject the electron through ionization, you can emit electrons, or photoelectrons they're called, of any energy, and at that point there is no longer quantization. So this general assertion that energy is quantized is just an overstatement. Okay, let's keep going. We now get to the black body radiation as fitted by Planck's equation. As you can see, it fits very, very well. And we have here a few explanations. So it says here, number one, the energy of a system can take only discrete values. I think that's an overstatement. Only in certain cases it can take discrete values. As we saw, the particle in the box, hydrogen atom, and even there are quantum oscillators like a vibrating molecule, and that way the energy of the system can take only discrete values. That would be correct. Okay, then quantized oscillator can gain or lose energy only in discrete amounts. That's correct. And to emit energy from higher energy states, the temperature of a quantized system must be sufficiently high to excite those states. Basically, the energy levels can be populated or not populated. To populate higher energy levels, you need a higher temperature. Okay. Moving along, we see here the emission of different gases. So what you're supposed to see in this figure 4.14 are, it's like light bulbs. So there's a top and bottom electrodes, and then they run a discharge. And depending on the gas, you see different colors. So we're all familiar with neon lights, and that would be the red light on the left. And then what the point of this was that it was observed that when they put hydrogen, you see these very beautiful lines, and they are spaced in a certain way. So here in figure 4.15, you have the lamp on the left, then it's taken through a prism. The slit just serves to make a kind of a narrow beam. And then you can see that after it goes through the prism, it gets bent, the light gets bent into different colors. And now we see two kinds of things. We have, in one case, the emission, and in part B, or the bottom part, we see the absorption. So if you pass white light and you then have an absorbing sample, then it absorbs discrete lines, okay? And then in the bottom, in figure 4.16, we see the emission of hydrogen, mercury, and neon. And what we see is that they have very discrete lines, and that these lines are very different. This could be useful, for example, if you have a light bulb, some kind of a gas emitting light, and you wanted to know what's inside. This would give you the composition, for example, right? Okay, so now we go back to this emission, and turns out that a number of people were trying to figure out what determines the spacing of these lines. And one of the ideas came from Rydberg, who found that the Balmer lines go according to formula 4.6, okay? What we see in formula 4.6 is we see a constant, in this case 3.29 times 10 to the, 15 inverse seconds, and that's because it's a frequency. But we see this 1 over n squared dependence, which in those days they had no idea why, but they could get that dependence only if they were dealing in terms of frequency or wave numbers, but not if they were looking in terms of wavelength. So this is a Balmer, that Balmer line. Then we go through here, and then I mean, in one of the concepts that we're going to be talking about, and definitely might show up in the exam, is absorption or emission of light. This is something that we discussed in class, and usually you would draw the energy, the relevant energy levels. That would be figure 4.17. In this case, there's just two levels, so we don't know what is the energy dependence between them. But if we're talking about particle in the box or hydrogen atom, I'm going to want you to draw the energy diagram and have the appropriate either n squared or 1 over n squared dependence. Otherwise, say, I will not be convinced that you have understood how the energy depends in those systems. Whether it's n squared or 1 over n squared depends on the potential energy. When the box, so to speak, has vertical walls, so to speak, as in the particle in the box, that we draw these straight lines, these straight vertical lines to where the energy goes to infinity, then in those cases, we have an n squared dependence. In the hydrogen atom, because the potential opens up very widely, right, as 1 over r, the potential goes as 1 over r, then the spacing of the energy levels gets closer and closer, as we will see so. Now, you may want to ask yourself, how is it that we know about the energy levels of atoms? Well, we know by two means. One is we have a way to look at absorption and emission of light in those lamps, as we saw a little bit earlier, but we also have this apparatus called the Frank-Hertz experiment. And what we see as the result from these experiments is that we see that every time the electrons match the particular energy, we see more and more absorption of, I mean, the electrons have let's say a bigger effect, and then so more light emitted, and then they stop emitting light once the electrons no longer match the energy difference. Okay, and so in this type of Frank-Hertz experiments, we see different peaks, as we see in this graph, and we see here, right? So there's more photons, and then it drops, and then there's going to be another one of this, and that would be the next energy level. Okay, And in figure 4.2, we have the energy levels, and we see that when the electron matches the energy, then we see these transitions. Okay? So we get a very important formula that we're going to use all the time. In this case, if you remember, E equals h nu. And so we see that that when we so if E equals h nu, then nu equals the difference. So we're going for delta E, which is E on the top minus E final minus the initial, and that will be delta E. Okay, and so again, delta E equals h nu, and so we get that nu equals delta E over h, and that's what we have here. Okay. And we have an example where we also calculate a wavelength associated. So you can review this example to get more information. Okay. What else? So in this example, we have actually in figure 4.21, we have two different difference energies, because we have three levels, and so there's two different delta E's, and we see the calculation of those. Okay, good. Okay, then we get to the Bohr model. In the Bohr model, basically, by then we knew that the energy levels of the hydrogen atom were discrete energy levels. We knew that from the emission of hydrogen lamps, but we couldn't understand why. And so Bohr was inspired by the solar system where the planets orbit the sun, and so he plugged in the equations exactly as if electrons, which by then were already known, were circling around the proton, just like planet Earth circles around the sun. Now, in this case, he could not make sense of certain quantities. He needed somehow to restrict the motion of the electron. And so, inspired by Planck with Planck's constant, he proposed that the angular momentum of the electrons, meaning how fast they're rotating, was quantized. And that quantization is in equation 4.1 or 411. Once we have 411, we can now predict what are the appropriate radius, so known as the Bohr radius, which we know, which we use quite often in future formulas as A0. Now, I want you to notice one thing. One of the reasons why we use A0 in the formulas that we're going to be, sorry. Okay, here we go. One of the reasons why we use A0 is because we want to save ourselves from writing all of these constants. And so when we use A0 is a way to getting all of these constants except for the n squared and over z, okay? By the way, this is a very useful thing in algebra and in quantum mechanics. If you want to write smaller formulas, you can associate a certain constant with, one constant can summarize for many others, okay? So with that, we get what the frequencies are and what the energy levels are, and we get a formula from Bohr's model that matches the formula from Rydberg and Balmer that explains the hydrogen atom emission. And that's all very cool, except for one thing, which is that this Bohr atom fails in a particular type of experiment done later. And so that turns out to be in need for further refinement. Okay, but here, so one of the very important things is this diagram, so I'm going to want to go into more detail. Okay, so one of the things that we're going to want to do is look at this figure. Okay, what is happening? In the vertical axis, we have energy. And then from the energy, we can imagine an axis here in the middle. Whoops, sorry that I'm not drawing very, very straight. But this axis is the energy axis. And then from here, we can imagine the radius, or the distance that the particular orbit would be from the proton. We would see that in n equals 1, the energy, this is the lowest energy, and so as Bohr imagined, the electron is circling around there. The next energy level is going to be 1 over n squared, which would be a quarter, right? So n squared would be 2 squared, it would be 1/4. So it should be 1/4 of this energy. So if more or less this is a half, then a quarter would be somewhere here. So we can imagine that this orbit is going around there. The next energy level would be 1 over 3 squared, or 1/9, and that would be this energy level, okay? And then one of the things that you should realize is that when n equals infinity, that means it's not that the n equals infinity level is not super high. Turns out that the n equals infinity level is here, right? Because this energy is 0. And so 1 over infinity equals 0, okay? Now, it is possible to excite from here to higher energy levels, If we do that, then the electron that is ejected has a certain energy, excess energy, delta E, okay? And that delta E energy is going to be equal to the energy of the total photon that we used here minus the energy from whatever level, let's say n equals 1 to 0, okay? This ejected electron is called a photoelectron. And so photoelectron spectroscopy allows us to make sure that the calculated energy levels that we are calculating here actually make sense. And so we can go to the experiment and measure them, okay? These photoelectron experiments are very similar to the photoelectric effect, okay? So that's an aside here. And I wanted you to understand this diagram, so I maybe expanded a little bit more than we should, but that's okay. And we have here, again, a calculation of delta E for, this is for the ionization energy. So E final would be 0, okay? And so E initial is this times 1 over n squared, but n equals 1, and so we only get this number, and this is the ionization energy of hydrogen, okay? If we multiply times Avogadro number, then we see the amount of energy to ionize a mole of hydrogen atoms, okay? And we have a solved example that I recommend that you check out. Okay, so we are then ready to interpret spectra of hydrogen, right? So we can put a lamp, and one of the interesting things is you might think, well, hydrogen is in n equals 1, so how can we get emission from any higher energy level? The thing is, don't forget that we are putting this in a discharge tube, so there's going to be electrons of with all sorts of high energies bumping into the atoms and causing the electrons inside of the atoms to be excited to a various different number energy levels from n equals 1 to, say, n equals 10. And so you can have emission occurring from all of these levels at the same time. And to calculate the precise emission lines, we would use the equation for 4.15. Okay? We can calculate the energy with 4.15. We can calculate the frequency with 4.16, and so on. Okay? And for absorption, then it's exactly the same thing. Okay? There's only, which one is the initial and which one is the final state. The main difference is that the initial state is lower than the final state in an absorption and the opposite in emission. Okay. Well, we get to part 4.4, which is the wave-particle duality, and this is okay. So yeah, this is de Broglie, and de Broglie is the one that postulated that any particle that has an associated linear momentum has an associated wave length, and these wavelengths become very relevant for very small particles, such as electrons, protons, atoms, and molecules, especially if they're very cold. Okay, so then we have in figure 4.24, we have different lines of hydrogen emission, and you can see here, for example, the Balmer lines, which are in the visible, and what energy levels they correspond to. Okay. Then we go to the photoelectric effect. The photoelectric effect was very critical to determine the energy of the photons, and that turned out to be very critical. In terms of the experiment, let's use the pen here. Okay, in terms of the experiment, we have light, and this light that is impinging on the metal we can control the intensity or the wavelength. Okay, what was found was that in order to get electrons ejected from the metal, you needed to get over the work function. So you needed energy greater than the wave function. And E equals h nu, and nu equals c over lambda. And so lambda needed to be short enough so that the nu should be high enough so that E would be high enough and greater than the wave function. So what was found was that if the wavelength was shorter than a certain value, you would get photoelectrons regardless of the intensity. Conversely, if the wavelength was longer, then independent of the intensity, you would get no photoelectrons. So that experiment was explained by Einstein, who got the Nobel Prize for it, and gave us E equals h nu, which later were named the photons, but not by Einstein. Okay? Now, we see more about the photoelectric effect, and we have the equation 4.18. Very well. We have a solved example. And then we get to the de Broglie waves, and we have the classical waves. And this is something that is very important, right? In the class, we looked at the solutions, and we also talked about taking an electrical cord and using these types of images here in the classical solution of the string instrument, that they will list n equals 1 higher than n equals 2 and n equals 3. It's just a lost opportunity in my mind. This should have been n equals 1, then n equals 2, then n equals 3, and then you could make an easier extension to the particle in the box, right? When we start talking about de Broglie waves, we look at the solution of the classical waves so that we begin to understand a little bit more about waves and conditions. We know from classical waves that the solutions are quantized, so only certain solutions are allowed, and that's given by this equation 4.19 for these vibrational strings. But one of the keys that are going to be absolutely important for any kinds of waves is the larger, the energy of each of the waves is going to be proportional to the number of nodes. More nodes, more energy. Okay, remember that. And then whenever you have a wave, a particular system that is going to be addressed by waves, such as the particle in the box in the hydrogen atom, that's going to lead to discrete solutions. That's no surprise of quantum mechanics. That was known from classical mechanics. Okay, and so here we have, for example, a circular standing wave, which is a closed loop, and that's something that we see in figure 4.13. And so they don't only need to be strings. It could be something like this. For example, if you have a thin metal ring, it would vibrate like this. And by the way, if you take a high-resolution video of a drum vibrating, you would see quantized solutions of the circular area. So here we have the solutions here for this ring, which kind of begin to tell us that the Bohr was onto something, right? Because here we have the discrete solutions for a wave in a loop, in a closed loop. You can imagine the electron traveling in a closed loop or an orbit, kind of like what Bohr was mentioning. Okay, so again, it's going to be important for you to calculate the wavelengths for a particular particle with a particular mass and velocity. However, I don't quite like to calculate the wavelength associated with a baseball because I think that that's kind of nonsense. The Broglie waves are useful for calculating things that are much, much smaller than a baseball. We're talking about, again, atoms and so on, okay? Now, the photoelectric effect just talked about how photons can cause a metal to eject electrons. But the Broglie's waves indicated that an electron in motion would have an associated wave. So there was a prediction that if you had electrons of a particular amount of energy, that they would behave as waves. But what needed to prove that was slits of the appropriate size, and where the appropriate size needs to be a little smaller than the wavelength. And in those cases, there would be diffraction, and one would see whether electrons really behave as waves. The evidence came from electron diffraction. So in figure 4.31, the book shows that X-rays actually diffract from crystals, and this was known, and you obtain these discrete points, and those discrete points tell you about the arrangement of the atoms in the lattice of the crystal. So the question was, can we see the same if we shoot electrons at a material? And so the figure 4.32 shows how the arrangement of the atoms can cause waves to either to constructively interfere or destructively interfere. At the points where they constructively interfere, you see bright spots, and everywhere else you see darkness. And again, we have more waves, and then finally we get to the experiment and we shoot electrons, and what we obtain is these bright spots, and the arrangement tells you about the pattern that the pattern of the atoms. You will see here some kind of a hexagon, and that's probably because the crystal is a hexagonal type of atomic arrangement, and this is silicon. Okay, so it turns out that the electron diffraction was done pretty much at the same time that de Broglie proposed this, and so people, as soon as they found the results from Davison and Germer, they knew that de Broglie was right. And if de Broglie was right, that meant that the electron behaves as a wave, and if the electron behaves as a wave, we should use a wave equation to understand the hydrogen atom. But that's going to come until chapter 5, okay? Okay, so now we have the uncertainty principle. The uncertainty principle, we're only going to consider equation 4.25, and basically the uncertainty is going to be the uncertainty in the x, or the position, times the uncertainty in the momentum, which would be b, is going to be greater or equal than h over 4 pi. We're not going to go into greater details of why or why not. And it here, as it shows, it has to do with if we're going to be measuring with photons, then in a large object such as a baseball, the photons have a minimal effect. However, with electrons, it can have a larger effect. And basically, it was the point that when we measure, we affect the measurement that we're making if we're measuring very small things such as electrons and so on. Okay. So then we have a calculation, an example 4.6, and if you follow this example, then you would be able to address any kind of problem related to that. Okay. So we were getting to the point that if electrons behave as waves, that we should be able to use a wave equation to calculate the hydrogen atom. However, in the hydrogen atom, the potential energy is very complicated. Well, it's 1 over r, and we don't not only have radius, but we need to worry about two angles, theta and phi, as we saw later, as we will see later. And so it's easier to start with a much simpler model that allows us to solve the wave equation for electrons that behave as waves and to develop a language of quantum mechanics with that. And so we're going to be using Schrödinger equation, and for that we're going to start learning about about the language. The key point is the wave function. What is the wave function? So just like for particles, we know, for example, if I want to know where a certain person is, then we give the latitude, longitude, and we assume that they're on the surface of planet Earth, and so that allows us to determine where they are. If in addition we know that they are traveling at a certain speed in certain direction, then we can say, for example, Jimmy is traveling from East Lansing to Ann Arbor, probably to see a game between MSU to U of M that's going to happen at a particular time. And so it allows us to determine positions and so on, so we can predict the future in a certain sense. When we're talking about waves, there is time dependence in waves. We're not going to be looking at time-dependent quantum mechanics in this course, but we are going to be ignoring the time dependence for one thing. And then the other thing that we're going to be doing is we're going to learn that we're no longer talking about the electron as a particle, so we cannot say where the electron is. What we're going to have is a map of the wave motion of that electron. So we now think of the electron as the plucked string in a string instrument. And we're going to define it by the number of nodes, for example, right? We said that no nodes is n equals 1, one node n equals 2. That's how we're going to define the electron, and that's all we can know about that electron, okay? It's going to be determined by the wave function, and nodes are going to be critically important, okay? We saw how a Schrödinger equation comes exactly from the classical wave equation, and all you need to do is inject de Broglie's wavelength, and then you get the Schrödinger equation, okay? We saw that the solutions for Schrödinger's equation are sines and cosines, and that is because of the second derivative of so the second derivative of the wave function is minus some constant times the wave function. And so if we have a sine, then the first derivative would be cosine, the second derivative would be minus sine. So we obtain the same wave function with a minus sign. Similarly with cosine, and the constants inside, 2 pi over lambda squared, the 2 pi over lambda must come from inside. So you can see sine 2 pi over lambda x. And then because we take the derivative twice, we get the square, okay? And so we end up with Schrödinger's equation, okay? Good, cool. And we need to, the presence of external forces comes as V of x, which is related to the force, and it's the integral of the force. And here we end up with a full Schrödinger equation. As you can see from this equation, if we make V of x equals 0, then it's very easy to solve. Or if we make V of x equals infinity, then infinity plus anything is infinity, and the only way to avoid all the infinities is to make the wave function be 0 everywhere, okay? So that's how we solve it. The validity of Schrödinger equation was very easy because Schrödinger immediately used it to solve the hydrogen atom, and that settled it, okay? So interpretation of the energy, well, okay. Yep. Okay, so now we come here to a further interpretation, and so when we have light, there's the amplitude of the electromagnetic field and the intensity of the light. We know that the intensity is proportional to the square of the amplitude of the electric field. And so in a similar way, we square the wave function to get the probability of I don't like to say the probability of finding the electron or finding the photon, because that goes back to the idea that the electron or the photon are these discrete particles that are flying around, okay? But basically, you need to square to get a real a real value. That's what you have to do. Now, one of the interesting consequences is the following. So, kind of like, what is the intensity of the wave function for, let's say, for the ground state of the hydrogen atom? And in that sense, well, the amplitude of the wave function squared needs to be equal to 1, meaning there is 1 electron. And so because of that, we use something called the normalization. So we normalize that total amplitude, or the probability, if you will, of having the electron being contained by that entire wave function, as the integral over the entire space of the model. In this case, we have only a model of x. But if we had a three-dimensional model, we would need to integrate over the 3 dimensions, and then that needs to equal 1. Okay? And that means that it's normalized. And so, okay, so now to solve the particle in the box, we're gonna bind the region where the electron is allowed to move in X. Okay, and so we're gonna say X needs to be somewhere in the where the model is gonna be, for example, in the particle in the box from 0 to L. Okay, and so here the particle in the box is one of the simpler models. So we go to the particle in the box. It's gonna be a one-dimensional system. And this diagram really shows a lot of the things that we need to understand. So the first thing is the energy levels. Energy is proportional to 1 over 2n squared. Okay, proportional to n squared, not 1 over n squared, just proportional to n squared. So this energy, if this energy equals 1, then this energy equals 4, and this energy equals 9. Right? Then we see that the wave function has 0 nodes, 1 node, and 2 nodes. Okay, so the number of nodes is n minus 1. Okay, so always the ground state of a quantum mechanical system has no nodes. Very interesting. And then the probabilities, or basically psi squared, is, again, we see no nodes, 1 node, 2 nodes. Okay, and just like in the Young's double slit experiment, we see these nodes. Okay, constructive and destructive interference. Okay, we get the solutions. Okay, and by x over L, we check normalization. And this is the full normalized solution. Once we have the solution of the particle in the box, we're able to solve for the energy. And we see is n squared h squared over 8ml squared. If we have transition between the energy levels, we have that delta E, or h nu, equals the, and here they are using absolute value, so that you, in equation 4.38, they're using absolute value so that you can, it doesn't matter whether you're going up or down, if you want to calculate the energy of the photon that's absorbed or emitted, it's always positive. Okay? But make sure, for example, if you're writing in an exam, that you say absorbed or emitted. Okay? That's the most important. Then they have this equation, probability of finding a particle between x1 and x2. Again, that's going back to thinking of the particle as if it was a little particle. And we really need to get over that. Particles are behaving as a wave. There's no probability of finding the particle, as indicated there. Okay. So then you can solve this example 4.7 if you want. It's useful. Again, we have this calculations, probability of finding the electron, and so on. Again, remember, the electron is not a discrete particle that you're going to find. The electron is behaving as a wave. However, if we shoot high energy electrons, then if the high energy electrons fall within the node, then they're going to hit nothing. And if they hit in other places, then they have greater chance of hitting the wave function. And that's really the better way of thinking about it. It's not the probability of finding the electron, but it's the probability of hitting the wave function that is being described by that electron. Here we have experimental evidence that indeed, if you have a small wire, that you get these discrete energy levels, and you get here the probability distributions, or the wave function. Okay. The particle in the box is a model that can be easily extended to more dimensions, and so you can do it in 2 dimensions, and you can do it in 3 dimensions. And the take-home message from this is that the number of dimensions determines the number of quantum numbers that you're going to use to describe the wave function. So for a 3-dimensional model, you have nx and y and nz, or if you're in spherical polar coordinates, you're going to need 3 different numbers, which will be n, l, and ml, as we will see later. So we can solve the particle in the box in more dimensions, 2 and 3-dimensional boxes. you get these cool wave functions. Again, the energy levels are proportional to the number of modes. Okay. So the cubic box. Here we have the more results of the cubic box. I recommend that you read the chapter summary, that you review the concepts and skills, that you go through some of the solved models, okay, and that you solve the cumulative exercise, which is one of your homework exams. So this ends the review of chapter 4.